All right. How's it going? And the final stretch here. A couple more weeks. So, feels like people are talking about all sorts of things like the extreme value theorem, the mean value theorem, absolute extrema, optimization. See some people nodding their heads, other people less so. So, yeah. Let's kind of do the things as opposed to saying all the things. So, the extreme value theorem basically says the following. For any function, if it's continuous on a closed interval, you get a max and you get a min. So if f of x is continuous on a closed interval, closed just means the interval includes the endpoints. I mean, it's a slightly more rigorous definition than that, but that's what we're going to go with. Then f of x attains a maximum and a minimum. Here's how we typically do this. For example, find the absolute maximum and minimum of f of x equal to x cubed minus 6x squared on the interval from 1 to 7. The closed interval from 1 to 7, right? We're including the endpoints, it's a closed interval. So here's the idea. We're going to find all the places where we might have a maximum or minimum. And to do that, we have to find two things. We have to find, well, to find one thing, the other thing will be obvious. So our candidates are going to be the following. Endpoints, so 1 and 7, and critical points. The critical point being where either the function's derivative is equal to 0, so maybe a point like that, where you might have a maximum where the derivative is 0, or a place where the derivative doesn't exist, like a cusp or a corner. Both of those are places where we potentially have a maximum or a minimum. So to find those, we're going to take the derivative of our function and set it equal to 0, slash see where it's undefined. In this case, our derivative is 3x squared minus 12x. We can see that that function is never going to be undefined, or that derivative is never going to be undefined. Right? The polynomial, there's no division by 0, there's no logarithms, there's no square roots, so we have no issues. We're going to set that equal to 0. We're going to factor out a 3x times x minus 4. And our critical points are going to be x equal to 0 and x equal to 4. Those are places where we might have a maximum, might have a minimum. And again, here we're talking about absolute or global extrema, not local. We'll get to in a little bit. How do we determine where we have a max or a min? We take these critical points as well as the endpoints of x equal to, yeah. So I meant for the interval to be from -1 to 7. So actually, this brings up a good point. If one of your critical points is outside of the interval, in this case, if I don't change the interval, 0 would be outside of it. We wouldn't actually test that point because it's not in the interval we're looking at. But I meant for it to be -1 to 7. I'm not just changing, I actually really did mean for it to be -1 to 7. Like that's how I usually write this example. So that's what we meant to do. So our endpoints are x equal to -1, x equal to +7. So those 4 points, we're going to plug back into the original function to see which one gives us the largest value, which one gives us the smallest value. So let's take a look. F of 0, by the way, this is a good time to, instead of, well, 0 is not that big a deal, but looking at this function here, it's probably going to be more convenient to factor it as much as possible as x squared times x minus 6, so that it's easier to compute these values we play with. So f of 0 is going to be 0. F of 4 is going to be 4 squared times 4 minus 6, which is 16 times negative 2, which is negative 32. F of 7 is going to be 7 squared times 7 minus 6, which is 49 times 1. Much easier than doing 7 cubed minus 6 times 7 squared. And then finally, f of negative 1 is going to be negative 1 squared times negative 1 minus 6, which is 1 times negative 7, negative 7. So here's what we would say. This function, f of x, has an absolute maximum at, let's see, the point where we get 49, right? That's our biggest output. So we're going to say we have an absolute maximum at 7, 49. And f of x has an absolute or global minimum at this point here, 4, negative 32. The point with the largest function value and the point with the smallest or most negative. You move it on. Of course. Yes. Sorry. Thank you. Not that we need to graph it to see this, but I just want to point out that if we were to graph this function, here's what it would look like. So the function x cubed minus 6x squared looks about like this. I missed my shot there. And that's, it's a vaguely like that. And we do have a relative minimum here at 4, negative 32. We do have a relative maximum here at 0, 0. And when I say relative maximum or local maximum, that just means this point here is smaller than or lower than the points next to it. This point here is higher than the points next to it. But in this example, we restricted our domain, right? We didn't have everything. We were stopping at negative 1 on the left and positive 7 on the right. So if we restrict the function to starting here and ending here, it's a little easier to see that, oh yeah, 49 is the largest possible output value we get. And oh yeah, negative 32 is the lowest possible output value we get. So that's our absolute minimum. And that's our absolute maximum. A few more language things here. We would say that the absolute maximum occurs, in fact, let me write this down. The absolute maximum occurs at x equal to 7 with a value of f of 7 equal to 49. So the maximum occurs at the x value, the value is the y value. Similarly, the absolute minimum occurs at x equal to 4 with a value of f of 4 equal to negative 32. Sorry. Question, yeah.
The derivative of the thing, or like the original?
The original function. So when you're testing for absolute or global extrema, we're always finding the critical points and the endpoints, and then plugging them back into the original function to see what thing has the largest value, what thing has the least value. Let's do another. Let me just keep track of things here. So let's say our function is f of x equal to x over x squared plus 1. And we're, excuse me, on the interval from 0 to 2. It's a good idea when you're asked these problems, and again, we're finding the absolute extrema. When you're doing these problems, it's always a good idea to mentally check that the function and the interval meet the criteria. Meaning the interval should be closed, okay, it is. And the function should be continuous, at least on the interval. Doesn't have to be continuous everywhere, but it does have to be continuous on the interval. This function certainly, in fact, this function does happen to be continuous everywhere because that denominator can never equal 0. It's x squared plus 1. So usual process here. We're going to find our critical points. We're taking that derivative and seeing where it's equal to 0 or undefined. Let's say that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. And I would probably simplify the top here. Let's say it's going to be x squared plus 1 minus 2x squared, all divided by x squared plus 1 squared. Simplifying the numerator, that's 1 minus x squared over x squared plus 1 squared. And I would factor the numerator as 1 minus x times 1 plus x, all over x squared plus 1 squared. We set that equal to 0, we're going to get 2 critical points. We're going to get x equal to 1 and x equal to -1. And this is actually a good example of how one of those critical points is not of concern to us. We don't care about x equals -1 because -1 is not in the interval from 0 to 2. So we're not going to worry about that. In fact, it would be wrong to consider it. We would be making a mistake if we thought about it. I will also point out this derivative is also never undefined, right? The numerator is always good to go. The denominator is never equal to 0, so we don't have to worry about this having any critical points where the derivative is undefined. Plugging into the original function, so we're going to look at f of 0, f of 1, and f of 2. And we're not going to consider f of -1. Sorry, I always say that to emphasize the not, but I feel like I'm just saying not like I'm negating a negation, right? We're not going to look at f of -1. End of story. So we're plugging back into the original function here. So f of 0 is going to be 0 over 1, which is 0. F of 1 is going to be 1 over 1 plus 1, which is 1/2. F of 2 is going to be 2 over 4 plus 1, which is 2/5. All right, so clearly 0 is the smallest. So there's our absolute minimum. Personally, when I'm describing an absolute max or an absolute minimum, I like to write the entire point. So I like to write that my absolute minimum is 0, 0. Or at 0, 0. And what's bigger, 1/2 or 2/5? 1/2. And if you need to, you either think of it as 0.5 and 0.4, or you can get a common denominator, that's 5/10, that's 4/10. Either way, that's the bigger one. So we have an absolute maximum at 1, 1/2. Yeah, question.
So when we're given a restricted domain, the extreme of the domain are always critical points.
Yes, the endpoints are always, so critical points might not be the exact right word to use, but we always consider them, right? They're always candidates for where the extreme might occur.
Oh.
Yeah.
If it's like x to the third plus 1, like you could get 0 and you can get.
When you, like if it was x over x to the third plus 1?
Yeah, I think you get like 1 over 0.
Well, so it depends. We'll actually, let's look at an example here real quick. But let me see what's in the chat here. Someone's writing something in the chat. 2 things actually. One of you can talk a little bit about linearization and approximation. I second that. Possibly. We'll have to, probably. I have to think about, linearization. Sure, yeah. Yes to linearization, maybe to approximation. Go away. There's so to answer your question with a couple examples. So the thing about this idea of finding absolute extrema is to use the extreme value theorem, the function has to be continuous on the interval, meaning it has to be defined on. So I just covered up my own papers here. 1 second. For example, yeah, let's look at that example. If our function was x to the 2/5 power on the interval from -1 to, yeah, sure, 32 is fine. I'll point out this function is defined on this interval. It's continuous on this interval. It's not differentiable on this interval, but that's not a requirement. Because if you look at this function, it kind of, in fact, I'm going to give away the game here, but that's all right. It kind of looks like this. Starting at -1, you get, if you get -1 to the 2/5 power, that's going to be +1. And then 32 to the 2/5 power is going to be 4. So it looks something vaguely like this. We've got the point -1, 1. We've got the point 32, comma 4. And we've got the point here 0, comma 0. And just looking at this graphically, we can all say, oh, look, there's a cusp at 0, 0. This function certainly looks like it is not differentiable at the origin. Let's look and see. So to find the critical points, we're going to take our derivative, which is going to be 2/5 times x to the -3/5, and see where it's either 0 or undefined. Now, graphically, I think we can agree that that derivative is never equal to 0. There isn't a place on the function where the tangent line is horizontal. So this is never equal to 0. But there is a place where this is undefined. So I'll point out that if you rewrite this in a little bit more of an obvious way, you can write this as 2/5 times x to the +3/5. We can see that this is undefined when x is equal to 0, because we get division by 0. So it is true that x equal to 0 is a critical point. And just like before, we're going to test these 3 or whatever, however many points we have. In this case, 3. And again, we've already kind of got the answer in front of us. We can see that f of 0 is 0, f of -1 is 1, and f of 32 is +4. Yeah. Clearly, 0 is our absolute minimum. 4 is our absolute maximum. To answer your question just a little bit more, we can't really consider a function where the function isn't defined somewhere on the interval. So for example, like if I said our function was something like, sure, 2x over x squared minus 1 on the interval from 0 to 3, we couldn't apply the extreme value theorem here. It doesn't mean that the function might not attain an absolute maximum or absolute minimum, but the theorem doesn't guarantee it, because this function, f of x, is not continuous on that whole interval. Specifically, it's not continuous at x equal to 1 and also x equal to -1. But that's a problem because 1 is in the interval from 0 to 3. On the other hand, it'd be perfectly reasonable to ask the question to find the absolute maximum and absolute minimum of that same function on an interval that did not include wherever it was undefined or discontinuous. So you could say, for example, on the interval from 2 to, I'm gonna regret this, sure, 2 to 6. That's a totally valid question we could ask. Question.
Yesterday in class, we started working on this,
Mhm.
but to plug in the critical points, we're not supposed to take the second derivative, right?
That's a different thing I think you're thinking of, which we will also try to talk about today. So there's two different things when it comes to extreme values or maximum and mins. There's absolute maxima and minima, where you find the critical points, plug them into the original function to see if it's an absolute max or an absolute min or neither. And then there's also local or relative extrema, where you're just trying to see if a particular value is locally the biggest thing, meaning is it bigger than the stuff next to it? And there's two different tests for that. There's the first derivative test and the second derivative test, which we will talk about. Yeah. I feel like that might be the next best place to go. Mean value theorem is mean value theorem. Let's hit the highlights. We have limited time. The mean value theorem is important, but there's also not a lot to do with it. So let's actually go ahead and talk about local extrema. Finding and classifying. So when you think about local extrema, or I should say, let me back it up. When you think about critical points, a few different things can happen when you find a critical point. You can either have critical points that look like one of the following, like, I don't know, 4 things. You can have a critical point like this, where the derivative is 0. You can have a critical point like this, where the derivative is 0. You have a critical point like this, where the derivative is 0. And they correspond to different things, right? One of those is a relative maximum. Excuse me. That one's a relative minimum. That one's neither, right? That's neither a max nor a min because it's not bigger than everything next to it. It's also not smaller than everything next to it. You can also have things where it looks like maybe this, like a cuspy kind of thing, or a cornery kind of thing. So you can get a relative maximum if your derivative is 0 or undefined. You can get a relative minimum if your derivative is 0 or undefined. You can also get neither if your derivative is 0 or undefined. So here's kind of the good / bad news. Anything can happen, right? When you find your critical points by taking the derivative and setting it either to be 0 or seeing where it's undefined, you don't really know if the thing you found is the maximum, minimum, or neither. So that requires further testing, either using what's referred to as the first derivative test or the second derivative test. And I'll just say blanket statement. I think the first derivative test is better because it's always conclusive. The second derivative test, although useful and especially useful when in 21C, you start finding absolute extrema of functions of 2 variables, then the idea of the second derivative test is super duper important. So that's actually one of the reasons we talk about it here. But I would say most of the time for like graphing functions, the first derivative test is better. When we're talking about optimization and trying to like a word problem kind of stuff and seeing if you have a maximum or minimum, then it kind of depends, and we'll try to address that probably on Thursday. Let's go ahead and look at some examples of this though. Sure. So let's start off with some easy examples. So typically when we ask questions like this, we usually word it as find and classify the relative extrema of the function, sure, x to the 4th minus 4x cubed. It's a good one. So the usual process for this kind of question is find the critical points first. So step 1, find the critical point. Technically we're finding the critical values because usually you don't find the second coordinate, you usually just find the x. But people kind of go back and forth between calling them critical values, critical points. So I wouldn't worry too much about it. So find the critical values or the critical points. So take your derivative, which is 4x cubed minus 12x squared. Make a mental note that it's never going to be undefined. The polynomial, we have no worries. Set it equal to 0 and then solve it. So let's see, I can factor out a 4x squared. I'm left with an x minus 3. So when I set that equal to 0, I either get x equal to 0 or x equal to 3. But we don't know whether they're maximum, minimum, or neither. And this is where I would say we're going to use the first derivative test, which we'll actually write down in a second, but I'm just going to use it first of all. So here's I think the most, the fastest way to do it, or the most kind of compact. There's a better word I'm looking for that I can't find. Oh, well, the least amount of work, getting it all done nicely. So take your critical points, put them on the number line. You have 0, and you got 3. And the idea is we want to try and figure out what the derivative is doing in each of the 3 distinct intervals broken apart by these critical points. So pick a number larger than 3. 5, 7, a billion, whatever. Plug it into your derivative, not your original function. Put it into the derivative and see, okay, if I plug in 5, I get a positive number times a positive number, so the whole thing is positive. If I pick a number between 0 and 3, like 1, positive number times a negative number, the whole thing is negative. Pick a number like -1, this part's still positive, this part's still negative, so it's still negative overall. If your derivative is positive, your original function was increasing. If your derivative is negative, your function is decreasing. Let's talk about some intervals here for a second. So I'm going to say a little bit more than we really have to here. So note that f of x is decreasing on the interval from -infinity to 3. We don't include the endpoints, or at least typically. Some instructors do, it's kind of weird. But most of the time when we talk about an interval where a function is increasing or decreasing, it's always an open interval. F of x is increasing on the interval from 3 to infinity. So if your function goes from getting smaller to getting bigger, did we bottom out, top out, or neither? Looks like we bottomed out, right? We got smaller, 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 smaller. We stopped getting smaller, we started getting bigger. Oh, we hit a minimum. So this critical point right here, that's a minimum at x equal to 3. And at 0, we don't have a minimum or a maximum. It's a neither. Here's a decent approximation of what this graph looks like. So the function is decreasing until we get to 0. And the derivative is 0 at 0. So it's going to flatten out at 0 just for a split second. And then it's going to keep getting smaller because it's still decreasing. And then at 3, we bottom out. We stop decreasing at 3 comma whatever. And then after that, we increase. So we can see, oh yeah, we have a relative and global, but we don't really care about the global part. We have a relative minimum at x equals 3. And we have neither a minimum nor a maximum at x equals 0. But the derivative is 0 at x equals 0. Or, not yet. We'll get there. So a relative minimum just means it's smaller than the things next to it, which this is. An absolute minimum means it's smaller than everything. So let me give you a contrasting example real quick. In fact, I think you might have missed it, but I'm just going to throw back actually to the example we talked about in the beginning. If you look at this function, x cubed minus 6x squared, which looks like this. This point right here, which is 4 comma negative 32, this is definitely a relative minimum. but it's not absolute because this function goes all the way down as far as you want. Similarly, this point here, 0, 0, is a relative maximum. It is higher than all the points immediately next to it. But it's certainly not an absolute maximum because there are points over here that are way, way higher. Right. So, but typically it should also be like the word should also be there, whether you're finding a relative or an absolute maximum. Like the problem should say what you're doing. But yeah, when you're asked to find, typically when you're asked to find an absolute maximum or a minimum, it's usually on a closed interval, although it doesn't have to be. So there is another theorem that kind of goes with this that says there is called like the extreme value theorem for functions that have one critical point. If your function has one critical point, if it's a minimum, then it's usually an absolute minimum. Like, for example, here's kind of the most boringest example you can possibly have, probably. The function is x squared. All of you know what x squared looks like. You can see where the absolute extrema is. And it is absolute, it's also relative. So taking the derivative, which is 2x, setting it equal to 0, you get x equal to 0. Using the number line, putting your only critical value on there, looking at what your derivative is doing, cool. If x is positive, 2 times a positive number is positive. If x is negative, 2 times a negative number is negative. So my function left of 0 is always decreasing. Right of 0 is always increasing. It has to be not just a relative minimum, but an absolute minimum, because everywhere to the left, the function's higher than it. And everywhere to the right, the function's higher than it, because everywhere to the left, the function is decreasing. And everywhere to the right, the function is increasing. So we have no choice if there's only one critical value. That the left side, right, if the left side is decreasing, the right side is increasing, it has to be both an absolute minimum and a relative or local minimum. Yeah.
It's like we're saying the relative minimum and where the maximum are gonna be.
Say that again.
So like you said it's on the interval from like 3 to infinity. That's kind of where it's gonna be.
So like in this previous one here, I was talking about where it's increasing or decreasing. So I was pointing out, and I'm really pointing out because often when you're asked these questions, you're asked to give the interval where it's increasing or decreasing. So I was pointing out that, oh yeah, this function is increasing on the interval from 3 to infinity, decreasing on the interval from negative infinity to 3. So we certainly have a relative minimum at 3 because the function was decreasing and then increasing. I'm kind of thinking of it. I'm often when I do this, I kind of think, oh yeah, it's just smaller than bigger, so it's got to be bottoming out at some relative minimum. Does that kind of answer your question? Okay. Let's not look at that one yet. Sure. Okay, so let's look at another example. Let's say our function was something a little less nice. Like x minus 3 times x to the 2/3 power. And what I would point out about functions where you see fractional exponents, it's pretty much a guarantee that the function is not going to be differentiable everywhere. You're going to have a place where the derivative is undefined. Often, not always, but often. So when you see a fractional exponent, you should be on the lookout for that. So let's find and classify the relative extrema. Oh, I said I was gonna, so after this, I'll write down about the first derivative test. So finding the critical values, we're gonna take our derivative. It's gonna be 1 minus 3 times 2/3 x to the negative 1/3 power. And leaving it like that makes it, well, especially not multiplying up to 3 times 2/3, makes it hard to find the critical values. So let's simplify a bit. So I will say, when you're finding these critical values, you actually do have to do a fair amount of simplification to make it relatively easy to find. This is going to be 1 minus 2 times x to the negative 1/3, or preferably 2 over x to the 1/3. So right away, I can see that 0 is going to make this derivative undefined. So certainly x equals 0 is a critical value. X equals 0 is a critical value because it makes our derivative undefined. It's not the only critical value, but it certainly is one of them. To find the rest, I really need to get a common denominator. And there might be other ways to solve it, but it's usually best to do it that way. So we're going to rewrite this as x to the 1/3 over x to the 1/3 minus 2 over x to the 1/3, or x to the 1/3 minus 2 all over x to the 1/3. And if we set that equal to 0, we're really just setting the top equal to 0. So we're going to get x to the 1/3 equal to 2. We cube both sides. X is going to be 2 cubed, which is 8. And then I'll also point out again, if you set the denominator equal to 0, you just get x equal to 0, which we already identified as a critical value. Something worth mentioning, which we'll see in the next example. To be a critical value, to be a true critical value, the value has to be in the domain of the original function. In other words, the function has to be defined. Hasn't been an issue so far, it's going to be in the next problem. So, x equals 0 certainly is in the domain of the original function because f of 0 is 0 minus 0. Right, but it's defined. 0 to a positive power is safe. 0 to a negative power is not. All right, let's do the usual thing. Put those critical values on the number line. I should say, put those critical values and nothing else on the number line. So far, 0 has always been a critical value. But if 0 wasn't a critical value, I wouldn't be putting 0 on my number line. I don't want extraneous information on my number line. So, again, we're looking at what the derivative is doing. So this is also why it's really important that you try to simplify this as much as possible so that when you plug in these numbers, it's easier to tell if your quantity is positive or negative. So pick a number bigger than 8, like 27. Why 27? Because I can take the cube root of it easily. Right, pick a number that's bigger and also easy to plug in. So far, it hasn't been a challenge. This one, we have to be a little bit more particular. The cube root of 27 is 3. 3 minus 2 is positive. Positive. So it's positive over here. Pick a number between 0 and 8. 1. So actually, I really want to point out, we cannot pick the actual endpoint because we know, right, we found 8 by setting the derivative equal to 0. So if you plug in 8 to the derivative, you're going to get 0. So pick a number not 0 or 8. I'm going to pick 1, a number that's easy to take the cube root of. Almost always, if I can't pick 1, I usually pick 1. Almost always. 1 to any power is 1. 1 minus 2 is negative. Bottom is positive. So the whole thing is negative there. Okay, now we have to do a little, so now on the other side, pick negative 1. What's the cube root of negative 1? Negative 1. So it's negative 1 minus 2, which is negative on top, negative on the bottom. Negative divided by negative is a positive. So our function is increasing, then decreasing, then increasing. Which means at x equal to 0, we have a relative maximum. And at x equal to 8, we have a relative minimum. Just to satisfy any curiosity, this function looks kind of like this. Yeah, it's kind of funky. You've got a cusp at the origin because the derivative is undefined there, and then it kind of looks like this. 8 comma whatever. This is 0 comma. We could find the other coordinate here. If you plug in 8 to this function, f of 8 is 8 minus 3 times 8 to the 2/3, which is 8 minus 3 times 4, which is negative 4. You could find that other coordinate. And often when you're graphing functions like this, you will need to actually find the y coordinate of your relative extrema as well. Okay, one more of these and then we'll switch gears. And they had something specifically in mind, but I'm not remembering exactly. I'd love to not screw it up. Let's see if it's over here. Sorry, there's one function I really just want to make sure I get to. Not you. I think I know what it is. Sure. Yeah, that'll be right. Okay, let's look at this one. F of x equal to. Sorry, I think it's that. Okay. Sorry, I'm just making sure I don't get it. If I get it wrong, it's gonna be terrible. Let's do x squared over x minus 2. Okay, first and foremost, this function is undefined where? 2. Okay, so when you see something like this, you'd be like, okay, 2 is off limits. It's not going to be anything really. Well, actually, what are we going to have it to if we were to graph this? A vertical asymptote. So we know that you can't really have anything other than a vertical asymptote there. Now we continue on. So yeah, sure. So our first derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And simplifying, we're going to get 2x squared minus 4x minus x squared all over x minus 2 squared. When you're simplifying these quotients, you almost always leave the denominator just as something squared. There's no value to multiplying it out. Simplifying the top even more, I get x squared minus 4x all over x minus 2 squared. And finally, factoring the numerator, you get x times x minus 4 over x minus 2 squared. And setting this equal to 0 / being undefined, I get either x equal to 0, x equal to 4, and x equal to 2. Let's talk about 2. 2 is not a critical value. I know I just wrote it down, but it's not a critical value. But I'm going to include it anyway. Because 2 is what I like to call a pseudo-critical value. We're not going to have a max there. We're not going to have a minimum there. It's not even defined there. However, it's still important. Because a place where the derivative is undefined, even if it's not in the domain, the function is going to have its behavior potentially changed. The derivative might change signs there. And function might go from being increasing to decreasing. So that's why even though 2 is not a real critical value, it's still important. We still include it. We still need to consider how important it is. And it's definitely going to go on my number line for my first derivative. Usual stuff. Pick a number larger than 4, like 5. Pick the most factored form you've got to plug it into because that's the easiest to see what sign you have. Positive, positive, positive. The whole thing's positive. Pick something like 3. Or you can start doing the other thing where, since it's really completely factored, 4 came from this factor, which was to an odd power, which means the sign's going to change. 2 came from this factor, which was raised to an even power, means the sign's going to stay the same. 0 came from this factor, which is raised to an odd power, means the sign's going to change. Or you can plug in points. Or you can plug in 3 and see that it's positive, negative, positive, so the whole thing's negative. You plug in 1, positive, negative, positive, so it's still negative overall. You can plug in -1, negative, negative, positive, so the whole thing's positive. Very expensive. Either way you want to do it's fine. I just like doing it the way where you look at the factors because it feels a little bit faster. So now, what's our function doing? Well, derivative is positive. That means the function is the function, not the derivative, is increasing, decreasing, decreasing, increasing. One of the reasons why I wanted to mention this important, not critical point, but still important point, is if we were asked about the intervals where it was increasing or decreasing. So this function is increasing on 2 distinct intervals from -infinity to 0, union 4 to infinity. This function is decreasing on two distinct intervals. Because the function is undefined at 2, we cannot include 2 in the interval of decreasingness. We have to break it up at 2 and say, great, it's decreasing from 0 to 2 union 2 to 4. In the previous example, we did not have to break it up because the function was defined there. It was this first example over here, just as a reminder. This one here, right, the function was decreasing from -3 to 0 and decreasing from 0 to 3, but the function was also defined at 0, so it was totally fine to say it was decreasing all the way from -infinity up to +3. Even though the function flattens out right there, the function is still decreasing, because all it means to be decreasing is you're getting smaller from left to right. Any 2 points you pick in this interval, the one further left is bigger than the one further right. And it is. So now, if we ask about classic linear critical points, say, great, we have a relative minimum at x equal to 4. We have a relative maximum at x equal to 0. So I keep saying I'm going to talk about this the theorem here. So here the idea. So the first derivative test is kind of the following. The first derivative test basically says if f of x has a critical point at c comma f of c, then we have a relative maximum if we could write a bunch of words, but honestly, what we should really say is a relative maximum if the picture looks like this. There's your critical point. Your first derivative is positive on the left, so your function is increasing, negative on the right, so your function is decreasing. So your function goes from increasing to decreasing left to right. We have a relative maximum. Similarly, we have a relative minimum if at your critical point, the derivative goes from negative to positive, or your function goes from decreasing to increasing. That's really the way I do, right? That's what I've been doing this whole time. Like, that's how I think of it. There isn't a better way to think of it, really. And then I should point out, you have neither a relative maximum or a relative min if your picture looks like this, where it's increasing on either side, or like this, where it's decreasing on either side. That's kind of the whole story of the first derivative test. The second derivative test. Okay, let's talk about the second derivative. I know there's linearization. I haven't forgotten about the linearization question. We're on a roll here, so it's coming background. We still have 30 minutes, yeah. So what about the second derivative test? Well, let's back it up a little bit. What does the second derivative even mean? What does the first derivative mean? We haven't even really talked about that. So first derivative of a function tells us about how f of x is either increasing or decreasing, which we've alluded to many times already. So I'll just point out, I know I've said it, but I should say it explicitly. If, that's a bad word to start with. I should say the following. F of x is increasing if and only if the derivative is positive. And similarly, f of x is decreasing if and only if the derivative is negative. These are theorems. They can be proved. I think they're pretty obvious if you look at a graph. I mean, so I should say, the proof is not obvious. Like the proof is actually kind of a pain in the butt, but they're relatively easy to see being true. If you graph something, I think I can convince myself pretty well that anywhere left of A, well, clearly the function's increasing. Look at it. And definitely at any point to the left of A, if you look at the tangent line, the slope of any tangent line is positive. So the derivative is positive. Similarly, between A and B over here, the function is decreasing. Slope of any tangent line is negative. And similarly, after B, function is increasing, slope of any tangent line is positive. So there's this very, very natural correlation between the sign of the derivative and the increasing or decreasingness or behavior of the graph of the function. So then the question becomes, what about the second derivative, or what does the second derivative tell us about the function? Well, let's look at an example or a picture really. Let's say our function looked like this. Yes, I'm thinking of x squared, but I'm not writing it down. So a few things I would say about this function. What would I say about this function? Good question. What would I say about this function? Well, first I would say the function itself is concave up. It's opening upwards. That's one way of describing upward concavity, although there's like 3 other ways of describing it, which I'll mention one of them I think is neat. Let's talk about the derivative. Kind of my favorite part. So for this function here, what's the derivative doing? And that's not a great question. When we ask what a function is doing, there's an implied as we move from left to right. So the question is, what's this function doing? I should say, sorry, what's this derivative doing as we let our x values move from left to right? So let's see. Over here, way on the left, the derivative looks pretty negative. As we move to the right, are we more negative or less negative? Less negative, okay. We move further to the right. Now what? 0-ish. Further right. A little positive. More right. More positive. So we went from super negative to 0 to positive to more positive. The whole time we were increasing. Okay. So we just said f prime is increasing. Okay. The function's increasing. What's true about this derivative? If a function's increasing, what's true about its derivative? Greater than 0. Positive. Exactly. So if this function is increasing, its derivative is greater than 0. All 3 of these things mean the same thing. Or better said, all 3 of these statements are equivalent. You could say the second derivative is positive. I could say the function is concave up. You could say the first derivative is increasing, and we would all mean the same thing. And then similarly, the other way, if it's shaped this way, you could say the opposite things, right? The function is concave down. The first derivative is decreasing because it starts off super positive, less positive, 0, negative, more negative. And then finally, the second derivative, well, since the derivative is getting smaller, its derivative, the second derivative, must be negative, which I should write as less than 0. Sorry, got carried away. Kind of cool. So then there's this idea of the second derivative test, which is a different way of checking to see if a critical point is a relative extreme, whether it's a relative max or relative min. But the bummer, and there's a bummer, is that it's not always conclusive. Let me show you what I mean. Let me show you an example of the test first before I show you how it's a bummer. So let's look. Sure. Let's say our function is, yeah, fine. X to the 5th minus, let's go 10x to the 4th. Sure, why not? Something relatively not terrible. So critical points, f prime is 5x to the 4th minus 40x cubed. Again, we should factor. We factor out of 5x cubed. We're left with an x minus 8. And our critical points are 0 and 8. And what we're going to do instead of, although we will come back and verify with the first derivative test, we're going to use the second derivative test, which I know I haven't told you what it is yet. But here's what we're going to say. We're going to say, well, cool. At these points, which are critical points, either we have something like this, something like this, or something like this. So let me ask you, if we have a relative maximum, is the function going to be concave down or concave up? Well, it looks like it's definitely concave down. Or if we have a relative minimum, it's going to be concave up. And if we have neither, this, we're going to have an inflection point. Okay. So the idea here is that you can take your critical points, plug them into the second derivative, and then if your second derivative is positive, you know you have a minimum. If your second derivative is negative, you know you have a maximum. And if your second derivative is 0, you're out of luck. You don't know. It's inconclusive. So let's take a look at the second derivative. F double prime of x is going to be 20x cubed minus 120x squared. You should factor out the 20x squared. You're left with x minus 6. F double prime of 8 is, I don't really care what it is. I care that it is certainly positive. So we have a relative minimum at x equal to 8. Because we know that we have a critical point, and it's either a maximum or something like this. But since the second derivative is positive, we know it has to be concave up, so it has to be a minimum. Right? It can't be something like this. You can't say, it's not like we're right there, and you're saying it's concave up, but you don't have a max or a min. It has to be at the bottom because the derivative is 0. That's the idea of the second derivative test. One second. On the other hand, unfortunately, f double prime of 0 is 0, which means the test, it doesn't mean we have an inflection point. It means the test is inconclusive. You could have an inflection point. You could have a maximum. You could have a minimum. We don't know. You got a question?
Is that the same as like the number line?
No, it's not. It's different. So the number line thing we're doing is the first derivative test. So, and again here, I think the first derivative test is superior, especially if you're graphing.
Isn't the results of the number line we're finding out if it's 8 but isn't that the same thing as the second derivative test?
No, it's not. The second derivative test is about the concavity, which can tell you about whether the function happens to be a max or min. If we go back and look at the first derivative test here, plugging in our critical points 0 and 8, picking a number larger than 8, the first derivative is going to be positive. Picking a number between 0 and 8, you're going to get a positive times a negative. Something less than 0, you're going to get a negative times a negative. So in fact, at 0, we would have had a relative minimum. Not would have, we do. Our function is decreasing no. I quit. Sorry. Our function is what? Increasing, then decreasing, then increasing. So we have a relative minimum at 8, like the second derivative test told us we did. And we also have a relative maximum 0, unlike the second derivative. Didn't tell us anything, right? This is inconclusive here. So the first derivative test is superior. The first derivative test tells us we have a relative maximum at x equals 0 and a relative minimum at x equals 8. Yeah.
Explain the point of the second derivative test.
So the point is that it offers a different way of showing something could be a max or a min, but it's not conclusive. So the point is kind of, so here's what I'd say the point really is. There's 2 points in my opinion. The more immediate point is that when you start optimizing things like with word problems, which you're going to do in a minute, maybe not today, but in a minute, like class-wise, it's often a pain in the butt to use the first derivative test because sometimes your interval is kind of weird. Like the domain of your function is limited because of what makes sense. And sometimes it's just easier, instead of trying to show that the first derivative test applies, to use the second derivative test. There's also another theorem which we haven't gotten yet about, like, so yeah, there's a lot of things so that's actually one place where it's really useful. Sometimes it's more straightforward to use the second derivative test to show that a function that you're trying to minimize really has a minimum, because for optimization questions, they'll often ask you a question like, given that this box needs to hold a certain amount of volume, find the dimensions that minimize the amount of surface area you have to use. And then you set up the function, you take the derivative, you set equal to 0, you find the critical point, but we don't know if that critical point is actually giving us a minimum or a maximum. So to actually correctly do the problem, we're supposed to show it's a minimum, which can be kind of annoying. And often the second derivative test makes it easier to do. The other place is in 21C, when we start talking about functions of 2 variables, maximizing, minimizing them. This idea of something being concave down and having a maximum, or concave up and having a minimum, is actually very important. And it's kind of the only way of doing it. So that's kind of the 2 places where it comes up. All right. So instead of doing what I want to do, so let's talk about linearization for a minute. Which, yes, we did kind of not really talk about ever. So linearization. What is a linearization? It's a fancy way of saying find the equation of the tangent with a little bit of extra. So, an example or two. We want to linearize f of x equal to, let's start off with something not terrible, the cube root of x at a equal to, pick a value close to something nice, a equal to 8. Okay, what are we actually doing here? All this says, really, in more plain English, is find the equation of the line tangent to f of x equal to the cube root of x at 8. That's the whole idea. You're finding linearization. Now, sometimes you're not given all that information, but we'll get there in a second. So to find the linearization, we need 2 pieces of information. We need a point and a slope. The point we're going to find by plugging in this into the function value. So our f of a is f of 8 is the cube root of 8, which is 2. The point of the place you're linearizing at should be a numerical value that is comparatively easy to plug in. And then we need the slope. The slope is going to be the derivative. So our derivative is going to be, let's see, our function is x to the 1/3. the derivative is going to be 1/3 times x to the negative 2/3. Then we're going to plug in our point of tangency to find the slope of the tangent line. So f prime of a, which is f prime of 8, is going to be 1/3 times 8 to the negative 2/3. 8 to the negative 2/3 is 4 to the negative 1, 4, James, is 2 to the negative second, is 1 over 2 squared is 1/4. So 1/3 times 1/4, which is 1/12. So then the equation of my tangent line is going to be y minus the y value equal to your slope times x minus the x value. However, we almost always rewrite it as the following. First of all, we isolate y. So it's going to be y equals f of a plus f prime of a times x minus a. And then instead of writing y, we write it as the function capital L of x. Capital L for linearization. So this is the general formula, but you should remember, it's nothing new, nothing fancy. It's just the equation of the tangent line written as so that we're isolating y, or the function name. So in this case, our linearization is going to be f of x, which is 2, plus f prime of x, which is 1/12, times x minus our a value, or point of tangency, which is 8. And most of the time, you don't want to do anything else here. You want to leave it like this. It is not in your interest to simplify this further. Here's why. Usually this question comes along with something like, and use it to approximate the cube root of 10. 10, sure. Let's do cube root of 11 just to make the numbers easier. So the idea is that this linearization is an approximation of our function. What we're saying is that the cube root of x is approximately this linearization for values close to 8. Close in quotes there because, right, close. Close enough. How close? Who knows? Close enough that you shouldn't have used a different point. So we can say, cool, the cube root of 11 is approximately the linearization evaluated at 11. And then you just plug in the value for x, and you get 2 plus 1/12 times 11 minus 8. Which is going to be 2 plus 3/12, which is 1/4, which is 2.25. Let's check and see how close we are. You actually calculate the cube root of 11 on the calculator. Why do I not know where any buttons on this calculator actually are? Good question. There we go. Sorry, brain. 2.22. Pretty good, right? Not a bad estimate for just finding linearization. So that's kind of the general idea of linearization, is you can use it to approximate things. Let's look at another example. Let's look at a more typical way of writing this kind of question. So if I was asking a question like this, I might phrase it the following way. Use a linearization to estimate 2.03 raised to the 5th power. Okay, I'm pretty sure it's going to be close to 32. Because I know that 2 to the 5th is 32. So here's the process. Identify a function that's going to work. So typically, your function should just be the same thing you've written down here, except replace the numerical input with the variable x. So our function is going to be x to the 5th power. Identify your a value. That is the nice, easy number that we're going to plug in that's close to the thing that's actually getting plugged in. In this case, a is going to be what? Show me on your fingers. Right. If you have to use a number of fingers, it's probably going to be 2. because that's close to 2.03 and easy to plug in. Then we need to find both the function and the derivative evaluated at that point. So f prime of x is 5x to the fourth. So then we can see that f of a is going to be 2 to the fifth, which is 32. And f prime of a is going to be 5 times 2 to the fourth, which is 80. Okay, write the linearization. The linearization is, I think it's good to write the formula the first few times. F of a plus f prime of a times x minus a. So in this case, our linearization is going to equal f of a, which is 32, plus f prime of a, which is 80, times x minus a, which is 2. Here's what we're doing. We're saying, for this function, which I'm going to draw very not well, at the point 2, we're finding the equation of the tangent line. And not you. So, want the thinner wall. There we go. And then what we're going to do is to approximate 2.03, instead of actually plugging in 2.03 to the function and getting the actual function value of 2.03 to the fifth power, we're going to plug in 2.03 to the linearization and you get a value that's a little bit off. That's your L of 2.03. It's a decent approximation. It's not off by a ton, depending on how close your values are and what your function is. And so to approximate 2.03 to the fifth power, we're going to say, cool, it's approximately equal to our linearization at 2.03. And that's going to be this function with 2.03 plugged in for x. This will be 32 plus 80 times 2.03 minus 2. I again want to point out, it really is better that I did not simplify this, right? I could have simplified this as something terrible like 32 plus 80x minus 160, which is, I don't know, negative 128 plus 80x. And then I've had to have calculated 80 times 2.03, which just seems kind of terrible. I'm sorry. Whereas if I just leave it like this and plug in 2.03, it's kind of easier to do the arithmetic here, right? This is just going to end up being 32 plus 80 times 0.03. That's not terrible. 80 times 3 is 240, and move the decimal over two places, so it's 2.4. This is 32 plus 2.4, which is 34.4. Not bad. It's certainly better than doing 2.03 times 2.03 times 2.03 times 2.03 times 2.03 5 times, right? The first time, not so terrible. The second time, it started to get messy. And so, right, let's compare, just for the sake of comparison, 2.03 to the fifth power. That's pretty good, right? 34.4, 34.47. I feel not bad about that. So that's the idea of a linearization, is that you can use it to approximate the value of some function at a place that's not easy to just calculate. Now, you might ask yourself, why would you do this when you have a calculator? Well, they didn't always have it, right? This was a process that was invented before calculators were a thing to actually approximate roots of functions or other things that were challenging to actually calculate. Yeah, but it does admittedly feel like a somewhat not super important process because we have tools that can kind of circumvent it. The idea does come back around. So you talk about linearizations of functions of two variables in 21C, finding the equation of the tangent plane. It's still not a terrible idea to think about, but yeah, it feels a little less important. You can also use it to I forget what the other part of that question was. Let me just remind myself here. Yeah. So an example of something you could use it for, time is short. sometimes you use this to do something like, sorry, great. Yeah, there you go. So here's a type of question people might ask. A sphere with a radius of 3 inches is coated with ice 0.25 inches thick. What is the approximate volume of ice? So you could actually calculate it using a calculator, right? The actual value would be, well, take the volume of the larger sphere where the radius is 3.25 centimeters. Maybe I should draw a picture. So here's my sphere whose radius is 3 inches. And then it's being coated with a layer of ice that's a quarter of an inch thick. And so to actually calculate it, you would just find the bigger volume minus the smaller volume. The problem is that's kind of gnarly, right? The actual value would be the volume with a radius of 3.25 minus the volume with a radius of 3, which is going to be 4/3 pi times 3.25 cubed minus 4/3 pi times 3 cubed, which just kind of sucks. Or you could use what's called the differential, where instead of approximating the new value, we're going to approximate the difference. So it's kind of like, instead of approximating the new value here, we're just going to approximate the difference without the 32 added on. So the way we kind of do this is you say, great, it's going to be the derivative multiplied by how much input change there is. So our approximation of the change in volume is going to equal or be approximately what we call the differential dV. And the way you find dV, the differential, is you take your derivative and you multiply it by the change in R. Or maybe more nicely written, V prime of R times delta R. So in this case, your derivative of your volume equation, I know it's time to go. If you need to go, go. Your derivative is going to be 4 pi r squared, which interestingly enough is the formula for the surface area of a sphere. And then approximating the change of volume, our delta V is going to be approximately V prime of 3, the easy value to plug in, times the change in radius. Here it's actually a really nice example, because what you're kind of saying is you're taking the surface area, which is whatever it is, and multiplying it by the thickness of the sphere, of the ice, to get approximately how much volume of ice. It's not perfect, right? Because it's not perfect, right? The surface area changes as it gets bigger, but it's a good enough approximation. Bless you. So we get this, which is going to be 4 pi times 3 squared times delta R, which is 0.25, which ends up being 9 pi. Sorry. Oh, good God, I'm sorry. Yes, you should feel free to ask that before we get to the end of class. So sorry. Here it is. Apologies. Sorry, I've written notes on the back of it, was looking at them and totally forgot that that's everything. But yes, in general, please don't wait till the end of, I mean, I understand, I appreciate your sort of before politeness, but I just forgot. I'm an idiot sometimes. If I forget, please ask. I mean to do it earlier in class. I just forgot about it. So yes, that's all I got. Thanks for staying to fill out. Thanks for being the captive audience I made you today, because I forgot to hand out the attendance form. But thanks for staying. And yes, I didn't mean to hold you all captive like that.